So what I will do, I will first tell you a bit about why humanity needs micro energy harvesting, what it's meant for. I will talk about thermoelectrics. This is what my company is doing, the converting to electrical power. I will explain the basic principles, and I will focus more on the thin film technology that we have and make some comparisons with the classical solutions out there. We will have a look inside an autonomous battery-free sensor. What do I need to create a battery-free sensor in terms of the electronics that I need? The end of the agenda is I will share as much as possible applications and project examples that I'm allowed to share with you. As well, I will give you feedback what is not possible with energy harvesting. And I highlight for the body heat, because in Asian regions I get a lot of inquiries about this topic, and I will share you my vision on that. So, a lot to do today. And the first thing what I do, I will start up with a demonstration. And I'm looking now for a beamer. Yes. So what I do, I'm going to put this device in my hand, and I will collect heat at the aluminium bottom plate, guide the heat through a generator chip of Micropelt, and this is called the heat sink. It's a radiator to transfer the heat in the ambient air here. And what I want to do, I want to create some electrical power, store that in a capacitor, and there is a small printed circuit board with a Texas Instruments MSP430 microcontroller and a CC2500 radio. I have my laptop with a receiver and some application software. Now I have two sensors. One I give to you. You're my victim today. And my question is, put it on your hand and slightly press it that the aluminium plate is having a good connection. Yeah. And what happened now is the heat collector collected, guided through the chip. Now is already active. So you really put it on your hand, yeah, like that. Otherwise it won't start. So this must be me. And what I see is I have a temperature difference by integrated temperature sensors. I have a temperature difference of about 2 degrees. 2 degrees. And roughly I am now creating tenths of microwatt. And with tenths of microwatt, we will see later, it is not so difficult to support our system, which is duty cycle. So most of the time he's sleeping, and once a second he activates himself for a very short time and powers on the microcontroller. Now, why you must be ill. We swap. Yeah, there he is. Is it okay with you? Yeah, you're cold hands, eh? Yeah, you really is cold hands. So that's explaining the principle, what we are going to do. And what we need in thermoelectric energy harvesting is a flow of heat. It doesn't help me to have an absolute temperature of 100 degrees or minus 20 degrees. I need a gradient, a difference, which before my outside skin and the ambient air maybe here is 23, right? So it is like a windmill. I need a flow of heat through that device. So thermoelectrics is absolutely not new. The principle of it goes back in the 19th century, 1820, 1830. Names like Thomson, Seebeck, and Peltier. And the devices themselves are existing for tens of years and used, for instance, if you have a NATO economy hotel in Taipei, you will find it in a small refrigerators. They are used as cooling devices, as heat pumps. Yeah. There are those devices called Peltier elements. and they are existing for tens of years. You will also find them in a USB computer, which don't work, but it's a funny thing to put it to your USB to keep your coffee hot or your tea hot. And also they are used to generate energy for equipment from the friends of NASA. Yeah. Now what you see is this classical device versus the micropelts. The micropelts you will see later are thin film chip devices, very small. And the purpose again is, if I look in the media and I read about the Internet of Things, I read about remote sensing, I read about machine-to-machine communications and dozens of buzzwords, my question is, okay, how are we going to power those devices? Can we do that with micro energy harvesting, using ambient output, which is only thermal what we do? It can be light, obviously solar. Indoor light here is a little bit more difficult. You can read that in this table, for instance, light outside. This is the energy density per dimension unit, which is outside superb. Inside it's challenging, especially here. And we have mechanical harvesting. We can have piezo, like with a mechanical. Think about the switch, like the company Ocean in Germany is doing. Switches to activate light. Yeah, and so today we will focus on the temperature one, the Seebeck effect here is Micropelt, and you can see already that the density of energy of a modern chip is much higher than from the classical Peltier devices. You often see those kind of tables in popular media, most of them. This one is the most recent one I could find from the University of Hamburg. So if you give a Google, you will easily find this list. Yeah. So how can we activate this sensor? Every project that we are in contains a microcontroller. Many projects include radio, not all of them. Imagine I have an operational counter for a machine, and the data is stored locally. There is no radio. That are pretty easy one, because radio usually eats the most energy in the equipment. In certain applications we see later, we even have a motor. It's also a challenging one. A motor eats quite some energy. So the purpose is, again, to replace this battery. And via this thin film technology, it's in the order of a milliwatt. This feedback here, I say a milliwatt. It can be hundreds of microwatt till 10 milliwatt, in that range. Say, well, 1 milliwatt is nothing. On the other hand, if you make an equivalent of 1 milliwatt based on continuous availability, just for the mindset, 24/7, which is 8,760 hours a year, you get a better feeling of how much battery this is. 2.5 AA batteries about. So a milliwatt in ultra low power and wide-use equipment is quite some. It's a lot. So a milliwatt, most applications eat much less, hundreds of microwatt in average. Of course, the peak energy is much higher. That can be tens of milliwatt or even hundreds of milliwatt. But we have to calculate in average, because you saw my demonstration as well. That sensor was mostly sleeping, and only once a second he wakes up for 10-50 milliseconds and then go in deep sleep again. And it is not so difficult nowadays with modern semiconductor microcontrollers to have standby currents of microamps or even nanoamps nowadays. The principle of creating electrical power from waste heat is called the Seebeck effect. What happens is that I have here semiconductor material, two of those cubicles, we call them legs, and two of those legs are put in electrical series. One leg is doped with free available energy carriers, and the other one with positive energy carriers. What happens now when we are guiding heat through this device, it is attracting those free energy carriers, and what happens is here they are bundling, and I get a voltage here. So in thermoelectrics we are a voltage source. I think solar is a current source, but we are a voltage source. And this is the effect defined by Mr. Seebeck. He says the output voltage is a certain material constant, which I can find in a table, linear with the temperature gradient delta T. Roughly, you will get 0.2 millivolt if you have those two in series, 0.2 millivolt, so-called thermal couple. So far, so good. So I now go more looking to that thin film. We have seen that thermoelectric Seebeck effect very briefly, but now we make the jump already to look into what is that thin film? What is Micropelt doing? Yeah. So what we do is we 6-inch silicon wafers. Unfortunately, the movie is nevertheless the movie, and we deposit thermoelectric material, bismuth telluride, with a thickness of 30 to 40 micrometer. So what we call thin film, not so thin, it is quite thick, but nevertheless we call it thin film. One wafer is doped with the positive energy, the other one is n-doped, negative, and we structure it with classical, let's say, photolitho equipment in micrometer. So we are not a company doing a very state-of-the-art nanometer structuring like the colleagues here of TSMC and UMC and those companies. We are having tens of micrometer kind of structure. End of the day, what we do, we flip chip them, those two wafers together, to create the end products. So that is the heart of the Micropelt technology. Yeah. Here you see it as well. Here you can see the depositing of the thermoelectric material, bismuth telluride. We structure the chip, adding specific material for this and to the end products. End of the day, the chips look like this. So it can be square millimeter, 10 square millimeter, maybe 15 square millimeter, but the smaller the better for us. If you like. Now, because we are having such small microstructures, we can put a lot of those legs, of those thermocouples, inside one chip. So our legs are 30 to 40 micrometer, compared with those classical Peltiers, they are a millimeter, or maybe half a millimeter, and maybe even a little bit smaller, but then it's getting very difficult. And the output voltage of a device is, as we saw, depending on that material constant and the temperature difference, but also the amount of the thermocouples I put in series. So the output voltage of such a chip, generator chip, can be more than 100 millivolt for 1 degree Celsius. And that makes it interesting for specific applications, like working from my hand is possible now. Yeah. Already now I have some hundreds millivolt to activate the electronics I need to upconvert the voltage, the DC booster. Here you see the number in the, I call it the large Micropelt device. We have 540 thermocouples. There are more than 1,000 of those legs on just the 12 square millimeter. And you see that the output voltage per square millimeter is a factor 40 higher than a state-of-the-art classical Peltier. Another question I sometimes get, I'm in marketing with purchasing people. They say, hey, that they read, of course, that tellurium is a rare material. It's in the top 7 of rare materials, which makes people nervous, obviously. Yeah, because worldwide we have a couple of hundred of tons production, including recycling, maybe 300 or 350 tons. Now the good news is that because we are so small, we only need 100 kilogram for so even there will be a kind of shortage, whatever reason, in our material cost is not having a major influence, yeah, compared to the classical way of creating those thermoelectrics. Here's also a nice macro view on those cubicles. Good. So what are the differences between the Peltiers, classical ones, and the thin film solutions? I would say, first of all, they do not really compete. There is an application for Peltiers as well as a Micropelt. If we need watts of energy, tens of watts or some watts, I would say take a Peltier. Don't go for the very small, tiny Micropelts. We are more in the hundreds of microwatts, milliwatts. If dimensions are important for you, take the Micropelt. If you say, well, I don't care about dimension, you also consider the Peltiers. If you have an application with a very small temperature gradient, you probably have benefits of the Micropelts because of the high output voltage. The thermal resistance has a bit to do also with the output power. We will see later that a classical device had very low thermal resistance, which means to make a really functional thermal concept, I have to match that heatsink with the thermal resistance of the generator. So I need a relatively large heatsink targeting the high power. And because of the high output voltage, which I can achieve with such a thin film generator, I can create a DC booster which is targeting much higher efficiencies compared to the classical way, where typical efficiencies are just maybe in the 30 to 40%. And next to that, if you look to the production, it's obvious that the Micropelts are like a semiconductor producer. On one wafer, we can have 1,000 of those chips. And they are created by etching, sewing, and flip chip bonding. Compared to the classical bulk Peltiers, they are mostly even handmade. You have to saw the cubicles and pick and place straight and then solder them. You make one device at a time. What we can do is we can structure the dimensions. We can change the feature size of the thermocouples. Imagine we have a certain application which is demanding electric behavior and thermal behavior. We can make a new mask set and create a specific device for a target application. So we can really scale the size of the device as well as the dimensions of those legs. Now, since not everybody is able to handle dies, because what you will see in the box, which is going around now, is a bare die, like a MEMS chips or laser diode, just a naked chip. So if you want to integrate it, you must have access to microassembly capabilities and wire bonding, because not everybody has it, or during prototyping engineering is not directly available. We have put the chip inside a package. Of course, every semiconductor device is in a package, like a CPU. It's a plastic package, yeah? But we need a perfect thermal design. So it's very tough to identify existing packages here. And what we did is we created our own. It looks very simple. It has an aluminium plate and it has an aluminium seal. And in between is a plastic ring. It looks very simple. I promise you that there has been a lot of engineering work behind this to make it performance-wise very good, as well as industrial ready. A thermal generator inside a package. And now every engineer can solder 2 wires and make a prototype by making a switch and a cold surface. In this table, you see some specific of the Micropelt devices, and what you see is the high Seebeck voltage, but also you see here already the electrical resistance. And later, when we talk about the DC booster, this topic will come back. For the classical bulk Peltiers, the electrical resistance is in the order of some ohms, maybe 2, 3, or 4 ohms, and we are factors higher. Yeah? And this is an impact later if you want to develop the electronics for your DC boosting. You can. Now, when I'm doing marketing, I'm the innovative marketing guy. I always get a question, well, not always, but depends on the audience. And they tell me, what is your efficiency, your conversion efficiency? And the question is obviously coming from solar, because in solar there is a race for efficiency. So, if I get a question, my answer is, I don't care. Now, you might be a little bit shocked, or you will say he's right. I will explain, of course, why and I'm doing that by this very popular graph of what we can find back in nature. And I can see here at the left side the efficiency. The efficiency in percentage. And here I see the temperature difference. And what we see now is the thermodynamic law of Mr. Carnot, and he's saying the conversion efficiency can never ever be higher than my green line. This is the limit. Yeah, so if I have a temperature gradient, what's indicated here, 700 Kelvin minus room temperature, my transformation efficiency is somewhere in the 50%. Higher is impossible. And this is true because if you do some research about efficiencies of like power plants, we weigh how much, half of it in heat and the rest in electrical power. The motor in a car, away 2/3, 60% of heat. Yeah. So whatever efficiency we are going to achieve is below this line. And now I'm going to introduce a material constant, a unitless material constant in thermoelectrics. This I will need later to calculate for you real efficiency, the real transformation efficiency from heat into. This is figure it, ZT, and you can maybe later forget about it, but it is a relationship between the Seebeck coefficient, this voltage I get for this particular, and the relation between the thermal and the electrical conductivity of the material. What's important to know is that value today is always below 1, except for certain announcements, institutes and universities, but commercially available today below 1. And I can also see here, at different temperature ranges, I should use different materials. That's why we and also colleagues of the Peltier devices are using bismuth telluride at room temperature, let's say up to 100 degrees. Everything you read in research for high temperature heat recovery is done with even much more possible materials than identified here. And of course we at Micropelt, together with German partners, we are also working in this field. So today we use bismuth telluride. The ZT simply is less than 1, which means now we see those extra lines here. And those extra lines is the calculation of the efficiency based on that parameter ZT. So I would say today I can achieve almost 10% at this indicated high temperature. Not higher. And if all the thousands of researchers in the world would be able to triple that somewhere in the near future, they didn't achieve that around 30 years, but let's assume somewhere in time they can do it, we could double that to 20%. But I would, if we have that kind of temperatures, I would take a steam engine. It's better. At least try that. So I don't see thermoelectrics play any major role in the creation of primary energy. Today, we are focusing here, remember, room temperature. Yeah. And at the high temperature is a lot of research, as mentioned, also at our company. Now what is now the efficiency here? Then I take from Wikipedia this formula. I can type it's a simple marketing guy, and then what I get is, hey, temperature gradient of 5 degrees. Very reasonable example, or 10 degrees. What often happens to us. I can get 0.2%. That's it. Theory. And if all the researchers in the world are able to triple it, wow! I get 0.4 to 0.8% efficiency. Thank you very much. So, waste of time. Because in the application itself, we throw away so much in a DC booster. We throw so much in the power management, in the voltage regulation, tens of percentage. So why the hell are we trying for this temperature range? To improve it. So that's why I say I don't care. Leave it. We are just provide some extra. And the big win is in the electronics which come after, but not really in the thermoelectrics. Nothing to win. And that's why this is my picture. We do micro energy harvesting, battery replacement. Yeah. If at high temperature, we can do waste heat recovery, but still to replace the battery or avoid kills to equipment that might eat tens or maybe 100 of watt. Absolutely not believe in thermoelectrics in waste heat recovery, despite maybe what other companies announce. But by theory, how to do it? How to be competitive? You don't see that. And that's some company, Micropelt, offering hundreds of microwatt and milliwatts to power wireless meters, actuators and sensors. And also what we do, not only offering those generators, but as a startup company, and because this market is young and for us too slow as a startup, we have been creating complete systems as well. This is the unfortunate reality. If you have a new technology, even when it's very much in focus, often in the media, so your destiny is also to demo or die, to showcase it's working, and even offering end products. We are in spin-off from Infineon Semiconductor. There is where we come from. From the late 90s, we were a project at the German Fraunhofer Research Institute, so the colleagues from the Taiwanese ITRI. Since 2007, we are our own company, funded by venture capitalists. That means today we are not selling in very high volumes yet. We are buying a brand new production line in the north of Germany. Here you see the picture. And those machines here are that other equipment where we deposit the thermoelectric material that are huge monster machines inside of wafers at the same time where we deposit all the layers that we need to make the device. In the meantime, we are more than 25 people, so we have been growing quite some. I remember maybe 1.5 years ago we were less than 20. So everything in respect, yeah. And that is obviously because of people we need in the production side. Alright. Where are we? I think this is my summary of the thin films. Yeah. So, efficiency, I don't care. We are just offering battery power. We saw that, maybe also interesting, the amount of rare material that we need is so that's not a real issue. We'll come back to the topic of the DC booster, which makes us in the agenda, it looks already in the middle, and it is 11, not so bad. So let us have a look into the electronics to create energy harvesting system, and I need more energy than the electronics. Yeah, that's very clear. And how much my sensor requires, I cannot answer. Yeah? It depends on many kind of sensor I have. How often he is sending? If it's once a second, he needs energy once an hour. Yeah? If he has radio, he has to broadcast meters, he needs drastically more energy, then it's only a short distance or no radio at all. Yeah. What kind of radio protocol I have? Do I have a simple point-to-point star network from A to B? Or do I have a mesh network where I have a protocol of a self-organizing network? Applications can be very sensitive for the data, so you need encryption. If you do encryption, you have to add overhead in your data load as well and CPU power for the quality of service. Do I need an error correction, or do I have a bidirectional radio to acknowledge that the data is received correctly? Example, a very simple temperature sensor without radio, without encryption, without anything, right? That is maybe the micro average. It's a very simple one, or like a watch. Maybe my watch is 1 or 2 microwatt. It's a solar watch. That's it. It's easy. Is an ultra low power wireless sensor. Maybe tens of meters, like my demo, but no additional overhead in encryption and error correction. Just simply point-to-point connection. If this sensor is active and it is transmitting data, in peak it will eat 20 milliwatt, but in average, in a certain duty cycle, maybe some hundreds of microwatt. Imagine an industrial sensor. Industrial wireless HART or ISA, which must be very robust, must guarantee that the data is transmitted and received correctly, which eat in peak for sure 5 watt. Yeah. We are talking here about watt seconds, what he needs. But still he's in a certain duty cycle. Yeah. So in average 5 milliwatt or 10 milliwatt. That's still possible with energy harvesting. Yeah, the trick is of course that we have to buffer the energy. We have to store the energy. Continuous operation and energy harvesting are no real friends, because energy is too high. I take a sensor running from 3 volt, the better obviously. I take 3 volt, eating 20 milliamps, active for 20 milliseconds, and the rest of the time below quiescent current of 5 microamps, which can be today much lower. So here's a duty cycle, 0.4%. Yeah, it's only active once in 5 seconds, and I can calculate I need in the active time current times voltage times time is 1.2 millijoule, and in the standby time I need some microjoules, so the total is 1.3 millijoule. So now I can see if I take the average energy in those 5 seconds, I have 255 microjoule a second, which is 255 microwatts. Hey, this is my first indication that micro energy very well fit. This is what I do. If I get a question or inquiry first, I try to calculate this figure. Yeah. A little bit stomach feeling, whether it makes sense. Yeah. Another example is I have a half amp piece. But what I did is I took the period time 12 hours. So this device is only transmitting twice a day, as an example. It can be a GPRS sensor, which only have to report by one SMS signal a measurement of long distance. To a joule, which is quite something. And because I only need 2 sessions a day, the average current is even less. First example, right? It's nothing. I can virtually operate this device from the heat of my hand, of my finger. So you might say, yeah, but that's an easy one. Okay, then let's play a bit with that period time. Yeah? With this example of eating half an amp of energy for 20 milliseconds, and you see that even when this period time is going down to a minute or even seconds, energy harvesting would fit. Yeah? It's a matter of collecting the energy in an energy storage device. And that is the reason that also in industrial applications we have a lot of attention. to replace the battery or to extend the lifetime of the battery. So, and it has wireless, not in all cases. There's a sensor and sometimes a motor. But let us have a look. I mean, here is a wealth of semiconductors. Much better than when we started this. It was not such a pleasure to find ultra-low power devices. Today it's so easy. I have not only Texas Instruments, but Energy Micro. I have Renesas, ST, Green Peak, Microchip. All those colleagues do have in their portfolio ultra-low power, probably one microcontroller even better than the other one. But the power supply itself is sometimes still a little bit difficult. Let's go step by step, have a look what happens here. Through have a voltage depending on the temperature gradient, and we get a very non-linear behavior of the voltage, which I have to stabilize. And then I store my energy in a buffer. I'm going to translate this very simple picture in a replacement diagram for the thermal resistance. So what we see, we have a hot side, we have a cold side. And in between I have thermal resistances. I put this like electrical diagram, very simple, like Ohm's law. The thermal resistance depends on my generator. In our case, it is usually tenths of Kelvin per watt. I have a heatsink. This is this radiator, which is transferring the heat into air. In some cases, I have also a source resistance. In most cases, I have a very good attach to my source. It can be hot water. It can be the metal surface of a motor. Yeah? So in that case, that thermal resistance in series with my generator is relatively low. In the example of body heat, it's very high. So later we will come back to real resistance. What we see here is, what we see here is that the relation between the thermal resistance of the generator and the path through his cold temperature, in my example is always a heatsink to ambient air, that relation is determining how much voltage delta T I have and how much voltage I get at my generator. Yeah. Now, if we would make an application with such a large thermoelectric device, then I have, in this case, 2 Kelvin per watt. If I take a very small heatsink from 20 Kelvin per watt, then obviously it doesn't fit. Because effectively, I only get 10% of my temperature gradient over the generator, and the rest is for that so-called heatsink. Matching between the thermal resistance of the heatsink and the generator. If you open a datasheet of a thermoelectric device, then typically what you find is a graph with a temperature gradient and an output power. The temperature gradient is always over that device. And that doesn't help me so much, because usually there are very promising numbers. Promising numbers in terms of if you have directly over the generator tenths of degrees, then the output power can be hundreds of milliwatts or even watts. But we saw already that in reality, if I have a hot surface at any temperature, that I have a fraction or a part of that gross temperature difference over my generator. That's why, if we have a look in the datasheet of a Micropelt device, we made 3 practical solutions by sizes of heat sinks. And we just publish those, which practically means that you get half or even less of your temperature over your generator, and the rest is due to the heatsink and maybe some losses in thermal resistances. So what we see here at 5 ambient, 50 degrees, I get half a milliwatt. 67 degrees, I am more than a milliwatt. The red line is a heatsink, 3 as this one, and you see I get double the output power. Just to make it practical. Yeah. And you see here that the output voltage is indeed very high. Yeah. And at already 40 degrees, my output voltage is hundreds of millivolt. Yeah. This is very helpful when we talk later about booster. So if you compare generators, be aware that the datasheets get very confusing if they talk about the real temperature gradient only over the generator. Yeah. Try to compare it apples with apples in a practical situation. So the DC booster is used to define a fixed voltage, 3.0 volt. And what kind of DC booster I'm going to use, it depends on my application. If I have like my demonstration from my hand, then the temperature gradient is low and also the output voltage is low. So I will do everything I can find electronically to get that DC booster started. If I have an industrial application or an application close to a pipe with hot water, then my temperature gradient degrees. And my output voltage is 1.52 volt. In that case, my DC booster can be very simple. It's like a diode and a capacitor. We are using today. One is a discrete solution. Quite standard, I would say. You can recognize here an oscillator circuit. So he is pumping the voltage to a certain point. The start of the DC booster with its impedance, how it matches with our device, the start is defined by this transistor. So our choice in this case is this transistor, and he will start at about 250, 300 millivolt, which means for us just a couple of degrees Celsius. Yeah. If you are able to improve the circuit, the DC booster earlier. Then we guide the energy in the energy storage device, like a capacitor, and we limit here the supply voltage to avoid damage of the capacitor. We will regulate the voltage, standard LDO, to the voltage we need, and here we see a comparator checking is there already enough energy, enough voltage that capacitor to activate that voltage regulator. Very simple, straightforward solution. At the other side we see a one-chip device from Texas Instruments, the BQ25504, and that has certain benefits obviously. For instance, if you are using energy storage device like a thin film battery, a thin film battery can be very sensitive to overcharging or deep subcharge. In discrete solution I can also manage that, but here everything is in. I can absolutely, with all kind of readers, the voltage levels need for protection, the voltage levels for the output, etc. And yeah, that is an alternative, modern alternative in a one chip. In applications where we need a lot of energy to do the sensing and transmission, we would need a capacitor, so this will be the place to use, for instance, supercaps. What we often do in applications is we are monitoring the value here. If we use capacitors, if we charge a capacitor, the benefit is, the negative side is it takes time to charge, but the good thing is I can see the voltage. I can measure the voltage. So in certain applications, to avoid any failure in the transaction, in the transmission, what we do, we measure that voltage, guide that to an ADC of the microcontroller, and we say, I'm sorry, I an action for you, dear host, dear receiver, because I simply don't have the energy. Or you make a kind of adaptive duty cycle. You simply wait until you have enough energy. So either we send back like an acknowledge, I'm very sorry, or you do a kind of mini sequence, not the full test. So it's a trick that we always do in an application where a capacitor is used. And as mentioned, that one chip, especially in combination with a thin film battery, is ideal. So no bothers anymore that I make a failure working with thin film batteries. Everything is covered by such a device. If you use such a device like a thin film battery, then the typical supply voltage is 4.1 volt. That is sometimes a disadvantage, because my sensor electronics will eat 2.4 volt, for instance. So I have to down convert again from 4 volt to 2.4 volt. Now the question is, for instance, how you do that. If I use a regulator, like this one, a linear regulator, then I throw away a lot of energy when the sensor is acting. When he is asking 2.4 volts, 20 milliamp, I am throwing away over that voltage regulator a lot of energy. So it would be better then to use a buck converter. So if the sensor is active, I use a buck converter, but a buck converter has a very high quiescent current. Damn it. The linear regulator might be some nanos amps, and the buck converter microamps or tens of microamps. So therefore you will have to open your suitcase of analog electronics and you say, look, why not putting those two in parallel or half in series? That by microcontroller you simply say which regulator is working when. These are challenges that we face, which you do not even have when you develop ultra low power with a battery. You don't even care. With energy harvesting, we have to look for additional tricks to get the energy consumption even further down than what you would do when you work with batteries. But the tricks are simply tricks. It's nothing new, but simply because of doing, you learn when it goes wrong or when it doesn't match. So, energy storage device, we always need a buffer. Now, what kind of buffer is difficult to say? I don't know your peak current. I don't know how much energy I have to store for one duty cycle, or you want to have to cover a period of a day without ambient energy. I don't know your maximum temperature situation, which can degrade your energy. So we use a capacitor, supercap, or thin film battery. It depends. I can only say that the thin film batteries, which are relatively new and upcoming, do have some promising features for energy harvesting. For instance, I can purchase such energy thin film battery pre-charged, which means that when I install the device and the ambient energy is just his first microwatts, the application can already work. It's like a battery, it's full. Second benefit I see is that there is no leakage. Well, the leakage is extremely low. Even when I have, for a long time, there is no ambient energy available, the energy will maintain in that device. I think that is, that's two. So we have seen problems that the customer says, I have an application with a very reasonable heat source, but when the heat source is gone, I want that this device works for a day, which means for me I need a lot of energy. I can also use a big supercap, but in this case you can see that this device, for instance, is 700 microamp hour. That's a lot. I can use that for just a couple of days to do a sensor. Obviously they are very thin as well. The size is, I would say, centimeter squared, maybe a little bigger, and still extremely thin. Good. Now, next one is I will look to examples of projects that we have. And it might be that you say, well, that example he shows has nothing to do with my world, but it might give you a feeling of what can be done with micro energy harvesting. We are starting with a European heating system. A European heating system is liquid based. We have piped hot water throughout my house, throughout a conference like here, and at the wall we have those big metal plates. We call them a radiator. And each radiator has a mechanical valve. You can open it and you close it. There are more than 1 billion of those heating systems in Europe, which means that if you come in your office in a meeting room, it's in the wintertime always too hot because nobody is controlling it. If you go in your hotel room, it can be much too hot, so the first thing you do is open your window. There is no intelligence in those mechanical. So the idea is, why not making those mechanical valves more intelligent? That at least you can work with a host here, a room controller, maybe with a timer, maybe with a sensor that the windows are open. Maybe is this hotel room. If not, why should the heating be active? We can purchase those in radiator valve with batteries, which is okay when I take it home. I need 7, install all 7, and once in a 2 year, I have to replace the battery. But my mother-in-law not, and especially in a hotel or a school or in a hospital or commercial building, there will be a disaster of battery maintenance. So there we come in and say, okay, take a very small Micropelt generator, a very small one, because the conditions are super for us. There is a lot of heat, close attached, very healthy to the heat source, and this is an example of a company, a German entity of Minebeya, Japanese company, combining anything with a microcontroller, with radio, plus with a motor, with a valve. So the whole gearbox is even in. Now you might say, yeah, but what do you do guys in summertime? Or what do you guys if grandmother's room is never using the heating? Yeah? That are all valid questions that have to be covered, like by solar, if there is no light, I have no energy. In our case, we have no heat, we have no energy, so you must work with certain tricks. Maybe you open the valve at a certain time, or maybe you still take with you some additional energy for those kind of cases. End of the day, if all energy is burnt, the system won't work. Yeah. So you must, at the end of the day, work with tricks to cover those difficult conditions, your worst case conditions. Yeah. So based on water, it's always good. Yeah. Certain countries, they have water heaters, especially for hot water, like Eastern Europe and Russia, even Northern China. Yeah. That would be ideal. You can consider automatic, like in airports and hotels, wash your hands. Maybe we cannot primary battery completely, but because hot and cold water are so close to each other, it is so promising for energy harvesting, and maybe we can extend the time of the battery. Yeah. Or about energy storage. Like I have 800 liter in my basement with solar, and there are wires by the installer between this storage and the house control. We can avoid easily the wires and the installation cost by a simple radio connection without batteries, because with batteries it's impossible, because somebody has to replace the batteries every so and then. An application that, in my opinion, did not get attention is everything around air conditioning and air channels. We don't have But an air channel for me is also very promising because we have the flow of air is moving, which is good in terms of thermal capabilities of a heatsink. Plus, it can be cold or hot, and I can imagine sensors which are contributing to the heating and air conditioning system by making use of additional sensors, or maybe measuring the air quality, what kind of gases are available. So that is a field which I can say is not really explored yet. I only saw maybe at a university in the US that they wrote a white paper. I didn't see any real commercial companies making a product out of that. Complete different the heat source here are those. Every building, also this one, big building, big hotel, factories in semiconductors or automotive, any factory in the world will have kilometers of copper in the basement to transport the electrical energy to the machines, to the departments. I am sure that a plant like TSMC, they must have 30, 50 kilometers of copper, I promise you. And for the facility manager, there is a headache, which is something burns out, which happens. Those copper bars are connected every so much meter or so with a bolt. That's common globally. And the way of doing maintenance is with infrared camera. So you have your own maintenance department, or you let an external company, and they make with a thermal camera your infrastructure once a year, once a month, in a data center installation of infrared cameras. So what we have done is we developed a sensor operating from a small piece of waste heat when a current is going through that copper bar, activating a sensor wirelessly. And the good thing is that it doesn't have to act maybe every 10 minutes is more than enough. So what I need gateways, of course, to receive all those signals. But the good thing is I can retrofit it relatively fast. Because I could also consider, well, why not I'm making coils and doing something there? But I don't have time. If I have maintenance time, in my switch cabinet, it must be ultra fast. So we created those sensors. This one, the first customer will be Schneider Electric. It's a French company. That's why you see the name on it. And it is really having the intention to avoid in the electrical distribution system. So what we need is we have multiple sensors talking with a gateway. And what we can do, we can either feed the data in the existing infrastructure, PLC infrastructure. Every factory will have existing infrastructure, or one can consider a web server. So I can have a look via a web browser. And this is to do then with an alarm function or predictive maintenance. One of the buzzwords is in America is CBM, condition-based maintenance. Do the maintenance when your assets or your equipment is asking for it. And that to avoid this kind of nice pictures. Now, as a startup company like us, it is very difficult to market a new idea. Because we say, okay, when that worked for electrical power distribution in factories and hotels and data centers, could it also work maybe for the electrical distribution over land? The electrical transportation of energy between a power plant and a substation. Can I use then the heat of the electricity cables, circuit breakers and the transformers and the capacitor banks? Because 5 to 10% is wasted. 5% between the power plant and the end user and substation is wasted in heat. Now it is very tough then to go to a big OEM, ring the bell and say, here I am, can I talk with your... it's very tough. So what you do is, in this case, we do a field test with an electricity provider, and that is EDF in France, which is the biggest one in Europe. and they have been testing the concept. Just the idea we have tested. And then we publish. So by publication you try to motivate the industry. Very difficult. And on top, this industry is extremely how you call slow, conservative, extremely conservative. But in terms of heat, there is enough heat. There is enough heat to say, okay, why not having maintenance in this kind of situation. Everything that moves creates heat because of the bearings. A motor has bearings, it's rotating, it can be a vacuum pump in a semiconductor fab. And in a vacuum pump I have to replace the bearings every 2 years. So if you are the facility manager of a semiconductor plant, you have to pay a fee for servicing to the vacuum pump provider. And he's laughing because he takes out the bearings and he's cleaning them maybe and reselling it again. Our idea was, why not making use of the waste heat of a motor or a gearbox or a robot and letting the itself user, I need maintenance. So what we did, in our innocence, years ago, certain companies and said, look, I have a wonderful idea. And we started in research. We started in research. There is no market, new technology, new idea. And in research, the engineers, and they say, yeah, there's a lot of heat in the motor. And yes, I can make a sensor activate once an hour or maybe twice a day. And when the feasibility was done, we learned, after talking also then with the marketing guys and the business unit manager, it was a bad idea. Because they hate that a machine or an asset is telling to the end user, I do not need maintenance, because they live from service contracts. So what happens is that even in your innocent as young company, you are competing business model. So the application itself is still very, very promising. So we have to change our promotion and marketing, trying to talk with an end user or a maintenance company or a sensor system integrator. But we lost in this one a couple of years. And we make many demos, like here. We had a 3D accelerometer integrated, very simple, thing via the serial interfaces, a MEM sensor to the microcontroller. When we get an oscillogram, we can do an FFT analysis. We have a temperature sensor, right? So it's not even so difficult. And in my demonstrations, this device was active once in 2 seconds. Because for demonstration purposes, I cannot wait an hour. So it was a very simple demo. And so in this field, we are rebooting more or less. It's just an example that how difficult it sometimes can be, even when you have the smallest idea in the world, that is not accepted as you thought it was. These are the power-hungry guys. This process out chemical industry, oil and gas. Wider standards here are hot and ISO 100. Maybe on SIGPI being considered. And what happens here is that such a device, like devices like Emerson in the US, Yokogawa, Japan, ABB in Europe, they have a 19 amp hour battery, it's this big, and they have it runs in 3, 4, 5 years, depending on the configuration of that device. This field is in certain cases maybe very expensive, or even forbidden, impossible. So that's why those guys are very interested in harvesting in general. Energy harvesting, and what we want to do is we have a device like here. It's like a thermal battery with a cable, and you can connect a cable to such a sensor. This is the goal of what we have. Here, like ABB, they fully integrated energy harvesting inside the sensor. The look and feel and the dimension of that sensor are exactly the same as it was with a battery. And the guy installing this sensor doesn't have a clue what's inside, a battery or an energy harvester. Yeah, of course he sees this green thingy here. That's the heatsink. So in this field we have done a lot of work, field tests like here in Shell in the Netherlands. Unfortunately it's relatively slow. So we are working with some partners already for about 5 years. You have to qualify a lot. And also we are participating, like in ISO 100, contributing to standardization activities. Without a standard it won't fly. So a lot of effort in this field, but end of the day, energy harvesting is a must here. Because battery maintenance is, what I mentioned, either too expensive or in many cases even impossible. And the good thing is that we have seen a lot of marketing from suppliers like us in this field, and field tests we have published, but we also see more recent applications of end users. This article is also in English in the meantime, where a facility or a factory in the UK is sharing his experiences with sensors which were installed for many months already in his factory, and that are good signals helping this technology to take off. We do a lot of publications, and I always motivate my friends and competitors in this ecosystem to publish success stories, because otherwise it keeps a technology item which is not, because everything you need is nowadays available. So publications do help us a lot in energy harvesting. In transportation, a couple of examples. Consider, for instance, a train. A train may access points, or how about tracking the wagon? There is no electricity. Yeah, maybe electrical train you have electricity, but for a wagon, or at the basis with the wheels, there is no. So the only alternative you have is to use a battery or energy harvesting, and therefore I see a lot of research ongoing worldwide to get energy out of moving trains. And you can say yes, mechanical vibration, because the train is shaking. That is the second one. This is getting very hot. Solar is getting more difficult, simply because of dirt and how do you guarantee that there is enough light? So it's either mechanical or thermal, or a combination of it. Yeah. We see research in automotive, but we know automotive takes a very long time, and the idea would be, do wireless sensor networks play a role in automotive? And like in Japan, they have a consortium and a working group specially on this topic. Not in Germany, but in Japan. And in principle, it sounds very easy because there's a lot of heat. So it's very straightforward to power a sensor. But I cannot predict whether it will be implemented or not. So, as mentioned, we see often applications starting with research. Very promising. The question is, will there be a standard? Will it be adopted? And it can be a very time-consuming aspect. Yeah. So this is my last example, and this is a consumer application called smart cooking. Cooking, in fact, we are doing for 2,000 years. We have a lot of heat. We start a fire, and we want the soup and the vegetables to boil. Yeah? Much less energy when we did it properly, because the water we are using too much. The water is always boiling or making a lot of noise, with the risk is coming out. Yeah. There was a study in Europe last year, and the study was related to energy consumption for cooking. We have in Europe those labels. So when I purchase a refrigerator or a dishwasher, then I have such a label, and I can say, okay, I'm very green oriented, and I can purchase the category which I like. But for cooking hobs, there is nothing, because there is no trick to reduce the energy until now. So in that study, it came out that 7% of cooking, and I think that's a global figure, not only for Europe, is used for. In Europe, calculated was a huge figure out of the report that is 8 power plants we use in Europe for cooking. Very simple. I have a cooking vessel with a lid. I have a sensor. The sensor talks with the cooking pot. And that's it. And inside the sensor, I have a temperature sensor. I have an acoustic sensor. The technology exists. It is tested by all Swiss and German qualification institutes, you must say, and it is proven I can save 50% energy. And if I reduce the water in my vegetables, I can even save 80% of energy. Now, the question is, be adopted, will it be successful? That's of course a matter of marketing of the system integrators who are promoting this, or by luck, by some kind of regulation. In certain cases, you might be lucky that in a country or European Union, they come up with a kind of regulation or some sticker helping the sales of such a product. This is already available today with a battery. So at the IFA, the IFA, there was by the company Renje a lot of marketing, a lot of video clips on YouTube, how you can see how this works. Disadvantage is I have to replace that damn battery quite often, once in 1-2 years. The good thing is, this is one of the most friendly applications for thermal energy harvesting. It's so simple, because the temperature gradient, for sure, 90 degrees at the lid, and the end, okay, you have a kind of cloud of heat, of course, but it is maximum 60 degrees. So with the smallest temperature generator I can make, we could power this, and we are going to do that and make it a kind of battery-free green sensor. It works for all cooking technologies, gas, electrical. It can work for a water cooker. So I hope by all those examples you might have some ideas what's possible, what's not possible. And I want to highlight for today body heat, because this is one of the most popular questions I get. It's also my fault because I always demonstrate it from my hand. And thanks to a lot of research done on this field, for instance by the friends of the IMEX, the research community in Belgium and Holland, they have written a lot of white papers about body heat. And you can see on the pictures, over years, it has been a lot of experiments being done. But the good, those guys that look at this picture here, that the amount of heat from a human skin, from a human body, is just maybe a 10 or 20 milliwatt, which I can get out of my body. And remember the efficiency story I had. Get 10 milliwatt out with an efficiency of 0.2%. You can already have some feeling of what's possible and what's impossible. And in most cases of inquiries I get, questions are based on existing equipment. And I have to keep on explaining it's impossible. Your state-of-the-art, low-power technology of today is simply eating too much. We are not in this field. If you really want to do something, we are not in the milliwatt range. We are not even in the 100 microwatt range. You must be microwatt. Then body heat could work. So why is working? Perfect conditions. Well, not you. You have cold hands, but I have hot hands, right? And here, cool. I had a big heat sink. So I was consuming probably more than 100 milliwatt out of my hand. So I could make this 100 microwatt. If you do it raw, it feels uncomfortable, by the way. I'm cooling down my body. And what are the difficulties in body heat? Well, first of all, here you see the serial resistance. This is the skin. The skin is very funny because it's adaptive. Right now, it's pretty good here, air conditioned. I think the thermal resistance could be relatively low. But now in Germany, where I live, it's snowing. Go outside, then the thermal resistance will get high. The body will avoid heat. Out of that IMEC studies, all those papers you can find publicly on internet, you can see that this resistance, Kelvin per watt, scales from 100 to 500-600 Kelvin per watt. Just ballpark figure. Hundreds of Kelvin per watt we talk about. That means it will be impossible to get a large heat flow here, because of this one. Now you can say, let's make a huge device. And I have got some inquiry from military activities. They thought that they can put the soldier full with those things. And I said, well guys, you are freezing your soldiers, right? It doesn't work. My statement is, if you want to do this, focus on a 1 square millimeter, like a watch. The watch is the dimensions I personally believe this could work. And also I need a small heat sink. What I'm showing here is impossible. So take the watch. The heat sink might be some hundreds of Kelvin per watt by accident as well. So what I have hundreds of Kelvin per watt for the heat sink as well for the source. So let's make a generator. And if I want to have a thermal generator with 100 Kelvin per watt, it would be the smallest one that you saw in a box. A device of 1 to 2 square millimeter only. That fits perfectly. And we would be able to output some tens of microwatt. So in that case it would work. In that case it would work. But if you want to do this, this has all been done. That funny research. But if you really want to do it, you need biomedical know-how. How about aluminium in my demo on my skin? Is that allowed? Is that good? Is it healthy? So what kind of biomedical material I have to use with a good activity? How the human skin is changing, by the way, when I'm sweating or when I'm outside. So it's not just an electrical engineering question of making a DC booster and programming it. What I often miss is that companies asking me this question have a medical background. What we need is as well then still the electronics know-how, especially because the temperature gradient is so small, and with the chip I only get some 20 volt out at tens of electrical impedance. So we need a new DC booster here, and I need a perfect thermal design. All the heat must be guided through the generator, and it must be also a good design. It must not look ugly and still have a good thermal concept. Last but not least, I need access to microassembly, wire bonding. I must be able to handle those bare dies. And with this situation, there is future for body heat. Also, maybe thanks to the introduction of Bluetooth Smart. Bluetooth Smart, available tomorrow everywhere, in all our smartphones and tablets, whether you like it or not, simply in. And now I can create sensors which only need 1 button cell battery a year. It's an average 10 microwatt. So for energy harvesting, a possible good fit. I can make all kind of funny and useless application now. A sensor in my coffee mug telling me via my iPhone, drink your coffee and nobody needs it, but technically it can be done. Also without batteries. An application which is not possible is, for instance, can I recharge the energy, the heat energy for my big ASIC inside my smartphone and power back the battery? That question I get all the time. Not only for smartphones, but simply because of that ASIC is burning watts of energy. And what happens is that I have to explain it then to the engineer who's asking me, because I tell them, look, you have a very hot ASIC, right? Close to 100 degrees on the case, and you have a certain thermal resistance, and you have a certain thermal design of your smartphone or of your tablet or whatever. And the thermal design is made to avoid that the junction of your ASIC gets more if I please. This is your challenge. And what you do now, you add here micropelts between the outside of your ASIC and your thermal design. So you're adding thermal resistance. You are destroying your slim, fancy, good-looking design if you do this. So you need to add heatsink later to get it working. Plus the efficiency story, right? I give you a milliwatt or some hundreds of microwatt for your application. That is a complete mismatch. It doesn't make sense to consider this idea. How much time is still? 10 minutes, huh? Okay. How to get started? If you say, I want to play with this, I want to make something out of it, my first question always is, what is your application eating? Yeah, we are going to measure that. I take an oscilloscope, serial resistance, and I here of energy during booting and also when he is going active. Well, this is a very simple application. This is a temperature sensor, but the way is the same. I measure the amount of energy I need. Yeah. Then the question is the quality of my heat source. How much energy do I have? What is the thermal profile over the day or over a week or even over a month? That is usually the most question nobody knows. Data logger. Test your heat source over time and identify the worst case situation. Yeah. The picture here is an eval kit of Micropelt, and it is the same one that I showed before in a demonstration. So it is a complete data logger. The software is with it. You record your measurement directly in a file on your computer. Yeah. So you can play around in many examples on many heat sources you might see. Yeah. The position of that heat sink. This is some practical information. This is wrong. Yeah. Horizontal here, because you get a kind of balloon of heat here. But you don't get a good performance. This is good. So it is vertical, and you have a kind, the air is going from going up. You have a very healthy situation here. This is also how we specify performance in datasheets. Yeah. So let us make now a virtual mechanical design. And I'm not a mechanical. I'm born as an electronics engineer. And let us make a mechanical design still. I have here a hot side with a pipe with water. So I make an adapter. I have a generator and I have a heatsink. Important to know is that every transient I have a problem. Even when you think this aluminium is perfect, it's not. There might be some tens of microns offset, or there might be some imperfections or particles. Yeah. So that's the most important aspect we have to take into consideration. So what we do, we make an adapter, and first of all, we add here some thermal compound. We know this stuff. For the ones who is playing around with electronics and CPUs, heat sinks, that white stuff you put in between. Yeah, that's enough. It's good. And then what we have to do, we need we have to connect that heatsink somehow to the hot side, to the adapter. So what I can do is basically I can use bolts, stainless steel bolts. Stainless steel because the thermal conductivity of stainless steel is not so good. Still there's some leakage, fair enough, but in many of our products we use this. Very simple. Yeah. So I attach then the heatsink via two stainless steel bolts with the other side. If I want to do it perfect, I use some plastic elements, some isolator rings. Yeah, we call it a spacer. I can even make a ring around it. Plastic, nylon. We are using some special devices. It must have a very poor thermal conductivity. And we can glue it then. Yeah, you can really glue it together. Yeah. Then we have this one here. Because now we have to get that heatsink perfectly on the generator. And also take into account tolerances. Everything. I have tolerances in the generator, in the spacer. Yeah. So I need a material with a perfect thermal conductivity and able to compensate some hundreds of micrometers. So what we can do, we can use a graphite foil, or we are using a elastic material. Example here is a material Sarcon of the company Fuji Poly in Japan. We can get in 300 micrometer or 500 micrometer. It's a very good thermal conductivity. Yeah, and by that we have a good design, mechanical robust, but still I can have, in certain applications, with a very hot heat source, I get radiation to the heatsink. Yeah. So if I really want to make it perfect, I need a kind of shielding here. Now, use a FR4 material, very cheap, and you can avoid somehow the red plus. Well, maybe you need a PCB for your electronics or your DC booster. Yeah. So this, you can see here an example. In the middle is a generator. The generator is connected by 2 wires to the PCB. And on the PCB we recognize here the Texas Instruments booster. We recognize here the position of the thin film battery and some after regulation circuitry. Yeah. And by then my mechanical design prototype is done, which comes then to my farewell story. If you have any questions, contact me afterwards now, or send me an email. You can also go to our website. We have a lot of information and booklets. Also, I have some hardware booklets here, but the booklets are also online if you want to remember all the ideas that I just showed. And with that, I want to thank you very much, and I'm of course available for any questions. Thank you.